Hi, this is Aaron Jerome again with another video, Jerome Electronics YouTube channel. Again, I'd like to thank the people who made this, helped me make this intro here, mycockpitview.com and Necessary Disorder. Today we're going to be talking about the next part in the Introduction to Number Series. This is part C and D, binary to hexadecimal to binary. You're listening to an artist called Howard Jones. Great music. He's one of those that can make every song sound a little bit different. This song is called New Song, and it is an instrumental only of that. And check him out, Howard Jones. He's a great artist. Okay, we need to get into hexadecimal and binary, and so we're going to move on. Okay, this screen is really just showing a summary of what we're going to be talking about. Don't want to spend much time on it, but this is a student handout, one sheet for 2 students. When they trim this and put it in their engineering logbook, what they have is a table where they can compare the different number systems. Okay, let's introduce what hexadecimal is. Not everybody has an understanding what hexadecimal is yet. I've seen hexadecimal a lot using just 3 symbols. I don't know if it's because my suspicion is that it's used this way in assembly language, which is in a language that uses hexadecimal. And it's convenient to use only 3 decimals. Anyway, we're going to use 3 digits to represent hexadecimal. We can use more. First, we're going to set up the column weights. We do this in every number system, as we mentioned last time. So in this, this is base 16, which means we're going to be using 16 different symbols. To make the column weights, we're going to give each of these 16s an exponent. The first one is a 0, the second is a 1, and the third is a 2. And when we resolve these or convert them to their base counterparts, they will equal 16 to the 0 equals 1, 16 to the first power equals 16, 16 to the second power is 256. If we used another digit to the left, it would probably, if I remember right, be 4096. We'll probably be using that a little later. So those are the column weights for hexadecimal. Each 0 represents a different multiple of 16, and this, of course, is the number 0 in hexadecimal. So let's count. In hexadecimal, this is a 0, this is a 1, this is a 2, 3, 4, 5, 6, 7, 8, 9. So we get to 9. We're familiar with that because that's just like decimal. But in hexadecimal, we have 16 symbols, and we've only got 10 so far. We're going to need another 6 symbols. So what do we do? Where do we go with these symbols? Well, a lot of people know, some people don't. The symbols we use are the alphabet. So the next symbol we're going to use is an A, and this A happens to be an uppercase, because a lowercase tends to look like a 0 in some cases. Same as decimal 10. So A is a decimal 10. B, notice we have put the B here as a lowercase because uppercase B, that looks like the number 8. This B then is the same thing as decimal 11. They have the same value. C, case doesn't really matter because an uppercase C looks like a lowercase C. Lowercase D is used to represent a 13 because an uppercase is a little bit like a 0. We don't want to be confused. E, uppercase, lowercase is round like a 0. F, generally use uppercase. In fact, really we always use uppercase except for B and D. Probably the easiest way to remember that. This is the same as decimal 15. Okay, now we've used all 16 symbols. What do we do next? In the previous rules that we learned in the previous video, we do the same thing. It's the same rule as all number systems. And if you haven't written this down, you should write it down now. Increment the next left column and start over in the column that maxed out. What will this look like? Well, if you're going to increment the next left column, that's 16. Under the 16 will be a 1, and under the 1 column weight, the F will become a 0. It will look like a 10, but it's not the same value as a decimal 10. This is the same value as a decimal 16. Notice there's a 1 under the 16. Okay, and this is a 17 in hexadecimal. What does the number 255 look like in hexadecimal? Can you think of it? Can you come up with it before I show you? Think about it. What does it look like? Well, if you keep 3 digits, it's going to look like the word off, because the 16 column is maxed out. The 1s column is maxed out. Maxed out means F's in both, because that's the last symbol in hexadecimal, the highest symbol in hexadecimal. So that's what a 255 looks like, but what does the number 256 look like in hex? Think about that for a minute. What does it look like? Well, we've maxed out those 2 columns, so we increment the next left column and start over in the columns that ran out. It's going to look like 100, but it's not. Its value is 256. Okay, so I understand that. Hex is commonly used by computer programmers. You don't need to write this down because we've already discussed it, even though it's red. Hex is commonly used by programmers, computer programmers, because computers like it better than decimal, and people like it better than binary. It's one of those happy medium languages that's easy to convert either direction. Hex means 6, decimal means 10. That's why we say there are 16 digits in hexadecimal. 0 through 9 is 10 of them, and then 6 more, A, B, C, D, E, and F. And notice there that the B and the D are lowercase. Kind of a tradition, a standard, probably not a hard rule, but it helps us to not become confused by thinking that those are zeros. So these represent decimal 0 through 15. Again, lowercase, so you don't confuse a B for an 8, and you don't confuse a D for a 0. Now, that table at the beginning, this is a good time to open it up. Most of my students by now have trimmed it and fastened it into their engineer's notebook. But here's what I want my students to do with this worksheet. First thing, I want you to label this first column as the decimal column. Then the next one, we're going to call that the binary column. The column after that is going to be labeled hexadecimal, and the last column is octal. Although the paper that you've put in your engineering notebooks has another column, this one doesn't. That last column will be used for something called BCD, binary coded decimal. You can list that in there now if you want, or wait till later. Either way, we'll be talking about it a little bit later. Next thing I want you to do is put the base, the alternative base name for each of these. So if decimal is base 10, can you think of what the other ones are called? Binary, base what? Base 2. Hexadecimal, we just talked about this one, base 16. You should have written that down. Octal, as in octopus. Octal, 8 legs. Octal means base 8. I also like to talk about the 3-letter abbreviations that we use quite often for each of these number systems. For example, decimal, sometimes we just call that dec. Binary, sometimes we just call that bin. Hopefully you're writing all these down on your worksheet there. Hexadecimal, even though hex just means 6, we abbreviate hexadecimal sometimes as hexoctal, oct. Then what I want you to do is fill out this sheet by counting in decimal from the next cell down to the bottom. So you would start with 0 and then continue 1, 2, 3. Hopefully you remember. If not, ask your neighbor next to you to help you with these decimal numbers. It's just the same number system you've been using since before kindergarten. Hopefully you remember it okay. Don't need too much of a refresher on it. Once you get down to row 20, let's start on the binary column. I'll get you started on that. The first row in the binary column looks a lot like the decimal column. It's a 0. After a 0, well, there's only two symbols, so we're going to go from 0 to 1. And then we've got to zero out that column and increment the next left column, which means we're going to have to add another place to put numbers so that we can continue. So you're going to be following this pattern all the way down until you get to binary 20 at the bottom. If you need more time, we can pause the video now. Coming back to the hexadecimal column, we're going to start hexadecimal and go clear to the number 20. So start hexadecimal at this point looks just like decimal until you get to 9. Beyond 9, it starts looking different. Pause the video and see if you can figure out how this goes all the way down to the bottom. We'll be showing it later, but see if you can do it. Okay, in the octal column, you need to think about that. In the octal column, we also start with 0, 1, 2, and 3. The thing is, it's base 8, so we will not use a number 8. When we get to 8, we don't need to come up with new symbols, but we do use the rule, increment the next left column and start over in the column that ran out. That means you're going to have to put a 1 in the next column to the left and then put a 0 in the column that we're using now. That will look like a 10, but it is actually the value of 8 in the octal number system. Pause the video here to see if you can figure this out all the way to 20. Okay, assuming that you have finished this, let's show the answers. I'm going to show them horizontally. This is the number 0 in every number system. Then 1, 2. At 2, binary becomes different. 3, 4, 5. Octal will be the next one to be different. 7. Octal does not use an 8 because it's the base 8 number system, which means we're going to increment the next left column and start over with the column that ran out, meaning that that next column will be a 10. In binary, we've expanded out to needing 4 columns to be able to express an 8. Hex and decimal are pretty much the same. Here's a 9 in all number systems. Interesting that a 10 in binary looks like a 10 in hexadecimal. In hex, a 10 in decimal. 10 in hexadecimal is A, so we've stopped using numeric symbols and started using alphabetic symbols. And then we're going to keep going with these. An 11 in binary looks like an 11 a little bit in decimal. Hex is a B. Octal is a 13. 12. This is a 12 in all 4 numbering systems. It doesn't look like a 12, but that is representative of the value in every number system. This is a 13 in all systems, 14 in all systems, a 15 in all systems. Now what's going to happen next is hex will go to 2 columns. Octal will go to, we maxed out the first column again, so we're going to increment the next left column and start over in the column that ran out. So a couple of things change here. Octal, the value for 16 in octal looks like a 20. The value for a 16 in hex looks like a 10. And the value for a 16 in binary looks like a 10,000. Almost there. We're going to 20, 17. This is a 17, the value of 17 in all number systems, 18 in all number systems, 19 in all number systems, and 20 in all number systems. I think I'll go a little further. Maybe 21, 22, 23, 24. Let's take a look at what the chart should look like then. I think your charts only went to 20. Okay, so this is what your chart should have looked like. Hopefully you've predicted all of these values. All right, so now we need to talk about something else. We need to talk about how to convert a binary number, to a hexadecimal number. Hexadecimal Seems complicated if it's new, but I promise this is easy. It's easier to do this than to fall off a log. Okay, so let's get us a binary number. I'm going to use a full byte of a binary number. Here it is, some random binary number. We're going to break this binary number, just put a little space between them, and break it into nibbles. So we've got 4 digits, 2 sets of 4-digit numbers. Okay, we're going to convert each nibble to its hexadecimal equivalent. What on earth does that mean? Well, take a minute to write the red words anyway. Make sure you've got this rule written down. Pause the video now if you need to. Okay, so we need that chart we just made to help you realize how easy it is to convert binary to hexadecimal. So we're going to take this first nibble on the left and we're going to convert that to hexadecimal. Often the leading 0 will be dropped and sometimes we'll keep it. What was that number again? That's 101. So on our chart we're going to find binary 101. There's binary 101. That is equivalent in value to a hexadecimal 5. We're going to bring that across for the first 10 digits, 0 through 9. It's like converting to decimal. It's pretty easy. But we're bringing that number in from the chart, and that means the value of this binary nibble is 5. Also notice that if you put column weights above it, it would be a 5. Now let's do this one. We're going to go look on the chart for a binary number 1011, that is binary 11, and we're going to find that on there. There it is, and according to the chart, that's a B. Do this often enough, do this enough times, you won't need the chart. But you should realize that on my tests, on my computer tests, you're not allowed to use a chart. If you feel like you need a chart, you can recreate one on your scratch paper after the test starts. Remember, this chart was not hard to make. So 1011, a binary value 11, is equal to base 16b. Let's go back there and draw that in. And so 1011 is a B. So really all we had to do to understand how to convert a 10110101 from binary to hex, break it into nibbles, find the value of each one on the chart. 1011 is the value of B, 0101 is the value of 5. Put them together, you've got the hex equivalent. It's not so bad. So now, in a second, I'm going to start the timer, and I'd like you to put in your logbook, your engineer's notebook, on a scratch paper, something. I want you to see if you can convert the binary number that I give you to a hex number before the 10-second timer runs out. You ready to go? Pause the video if you need some time to get ready for this. Okay, here we go. Convert this binary number to hex. Use your chart until you realize how easy it is to make these conversions. Go. Okay, time is up. What did you have? Did you get it in 10 seconds, or are you still struggling to figure it out? This is an F4. Notice all the ones are maxed out, and of course, on the right side, there's a 1 under the 4s column. That means it's a 4. So you could just convert these nibbles to X, which is easy to do. If it's greater than 9, you might have to use the chart. But if you can quickly decode a binary nibble that is smaller, 9 or smaller, it becomes a little easier. Okay, let's try another one. This time you have only 8 seconds. I'm going to give you a number, and then I'll start the timer. You see if you can figure out the value of the number before the timer completes. Here's the number. Time is up. Hopefully you figured this out. I looked at the first one, 1001. Well, that's a 9. 1 in the 8s column and a 1 in the 1s column, that's a 9. 3 1s in the 4, 2 1s column, that's a 7. This is a 97. Of course, we could have just gone to the chart, but I didn't think it was necessary. It might be a little faster if you can do this in your head without looking at the chart, but you can use the chart if you want. Let's do another one. This one you only have 8 seconds to do. See if you can do it in 8 seconds. So the number is 11010010. Okay, time is up. The first one, that's 8 plus 4 plus 1, that's 13. So 13, A, B, C, 9, 10, 11, 12, 13, A, B, C, D. So 1101 is a D, and the other column is a 2. This is a D2. So hopefully you're catching on to how I'm doing this without looking at the chart. And I am doing these in the time allotted when I do them. Again, 1101. If I think about that, I know that there's a 1 in the 8s column, a 1 in the 4s column, that's 12, and one more is 13. Then I go 9, and then I count on my fingers, 10, 11, 12, 13. I got 4 fingers up, A, B, C, D. That's how I knew it was a D. Let's try another one. Okay, go. Well, the nibble on the left is a 10-10. That's a binary 10. That's an A. The one on the right is a 8 plus a 2 plus a 1. That's an 11. So if it's a 10 and 11, that's going to be an AB. Hopefully that made sense to you. Okay. Let's go backwards. I will give you a hex number, and you put the ones where they go in the binary number. Convert the other way, from hex to binary. I've set the clock to 10 seconds this time because this is the first time you've ever done it. Maybe you need a little extra time. Feel free to use your charts if that's what you want to do. But remember, you're going to take that hex number, which will have 2 symbols, one on the left and one on the right, and convert them to binary. Ready to go? Here's your number, 57. Okay, on the left, a 5 is a 4 plus 1. So we're going to put a 1 under the third digit and 1 under the first digit, and that's a 5. The other one is a 7. That's a 4 plus 2 plus 1. 4 plus 2 is 6 plus 1 more is 7. Hopefully that made sense. Hopefully 10 seconds was enough time. Let's do another one. 10 seconds. See how you do on this one. The number is, I speak the number in decimal, but it's really a hex number. Convert this number. This is a D2. I guess I did speak in hex. Okay, so a D. 10, 11, 12, 13, A, B, C, D. So 10, 11, 12, 13. I'm going to need to make a 13 on the left one. That would be an 8 plus 4 plus 1. On the right, just 1, 1. And that is my binary version. Hopefully this is making sense to you. Let's do another one. This time, only 8 seconds. Convert from hex to binary the number. Now this is from hex to binary. The number 6E. Okay, for a binary, a 6 is the 2 middle ones, so it's going to be 0, 1, 1, 0 on the left. On the right, that's an E. That's 1 before F, right? And F is fully maxed out. That means the first, or the 3 digits on the left will be 1s, or in other words, 1, or that's 8 plus 4 plus 2. 8 plus 4 plus 2, that's 14, and E is a 14, because F is 15, that's the highest we go. As highest we count to 0 through 15 is 16 digits. Okay, so hopefully that made sense. So let's do one. Let's ramp it up a little bit. Let's try this one. I'm going to go for 3 hex digits, and I want you to try to convert those to binary. It is 3F7, no timer this time. See if you can do it. First of all, I'm going to lay out the nibbles, the binary nibbles, and then I'm going to convert them one at a time. Pause the video if you need time. Okay, here we go with the answer. We're going to start on the right side and convert that 7. Remember, a 7 is a 4 plus 2 plus 1. That would be the 3 digits on the right, all becoming ones. F, if you remember, F is the highest number. That means all 4 digits are maxed out. F is a 15, and a 15 is a binary. 8 plus 4, that's 12, plus 2, that's 13, 14, and 1 more is 15. They are all ones. A binary 3 is just a 2 plus a 1. That's the last 2. So now I'm hoping that you kind of get how easy it is to convert hexadecimal to binary and binary to hexadecimal. Just divide it into nibbles and then make your conversions. Use the chart if you need to, but after a while, it becomes intuitive. Okay, now notice that I pressed these numbers together, the binary or the nibbles together, and now there's 3 times 4. That's 12 different symbols there. When you answer questions on the computer, I just need to point out that if you put a space between different nibbles, it will crash my testing system. It doesn't know what to do with that. So when you give answers, be sure not to put that space between the nibbles. Okay, and sometimes we drop the leading zeros, and so this is the value of 3F7 hex is 111111011 in base 2 binary. Okay, that's it for now. We want to maybe talk a little bit about what we'll be talking about next time. So this again is Jerome Electronics. But next time we're going to be talking about the subject of, it's a continuation of number systems. We've already done part A, part B. That was the first video. The second video was part C, part D. The third video will be part E, and in that we'll be learning how to convert any number system to the decimal system, how to convert any number in any number system to the decimal system. Thanks for watching. I will see you next time.